All right, guys, welcome back in to another video. Today we're going to be going over forces and motion, okay? And we're going to talk about forces like as you push things or you can pull things, okay? It's actually the definition of what a force is. A force is a push or a pull on an object, any push or pull on an object, okay? That push or pull can cause an object to start moving, stop, change direction, or change speed. According to Newton's second law, force is equal to mass times acceleration. So we can't talk about force without mentioning Newton's law. So let's scroll over here, okay, and let's go over them. Newton's first law says an object in motion will stay in motion unless acted upon by an external force. This is also known as the law of inertia. Newton's second law, where we get our force equations from, is force is equal to mass times acceleration. And then lastly, Newton's third law says for every action there is equal and opposite reaction. So knowing those laws can help us understand how forces interact with objects and how objects interact with each other. So that's the basis of everything we're going to talk about today. They're all described within those three laws. Moving on, I want to talk about four specific types of forces. There's a lot more types of forces that deal in their own specific world, like electrical forces, buoyant forces, but we're going to talk about four main types that you see in everyday life. Let me scroll over here. So the first one we have here is gravity. I'm sure everybody's heard of gravity. Okay, well, gravity is an attractive force between masses, two masses. So it's a force that attracts smaller masses to larger masses. That's why everything on Earth is pulled towards the center, because Earth is a very massive object. It is more massive than anything else that is on Earth. So therefore, everything is getting pulled towards the center of Earth because it is so massive. That's why everything does not float away. So knowing gravity, gravity has a bunch of cool constants with it that we can use to help us solve some formulas, help us solve some problems, use them in different formulas, and contextualize a lot of things. So let's get into that. So we'll scroll down here. All right, the first thing we need to note is that the value of gravity on Earth is 9.8 meters per second squared and is represented by the letter G in all of these formulas. Notice how gravity is an acceleration. That's the same unit as acceleration. So what is force? Force is mass times gravity. So in our formula for weight, your weight on Earth in newtons, any object's weight on Earth in newtons can be expressed by its force. So if we just take the object's mass and multiply it by Earth's gravity, lowercase g, we can get the amount of force that that object has pointing down towards the Earth. Okay, better known as the object's weight. This is why people say an object's weight and mass are two different things, because an object's weight is dependent on the gravity that it is in. The second way we can use gravity is through Newton's law of universal gravitation. Okay, this is a constant and is represented by the letter capital G in our formula. The constant value is going to be 6.674 times 10 to the negative 11th Newton meters squared divided by kilograms squared. Okay, that's a lot of units. It cancels, you'll see in the formula here, it's going to cancel a bunch of them out, and we're just going to be left with newtons there at the end. right, so let's scroll down here. Let's look at our universal gravitation formula. Ooh, let me erase that. Don't need that. Okay, so these are universal law of gravitation is how we describe the force, the attraction force between two masses. Because I remember we said gravity is the attraction between two masses. Things with smaller masses are attracted to things with larger masses. So we can measure the force of their attraction between each other using this formula. So let's go over the formula. So it's going to be force is equal to the gravitational constant times the mass of the first object times the mass of the second object over how far away they are, the radius, squared. So that will give us our attraction force between two masses. So that is basically the gist of gravity. It's going to come up a lot in our example problems. It's very important to know and understand how it works so that we can understand these other three forces we're going to talk about as well. So let's move on to the next force. Let me scroll back up here. Keep scrolling. Okay, the next force we're going to talk about is something called the normal force. This force occurs when two objects are physically touching each other. So imagine a book on a table or a backpack on the ground. Anytime two objects are touching each other, there's a normal force acting on the object that is sitting on top of it. The normal force opposes gravitational force. So it's going to help keep objects upright and not crumble. So if there was no force opposing gravity, we would all crumble towards the center of the earth. So these normal forces help keep us upright and not crumble and bad things happen. So here's what it looks like in a force diagram. We're going to get into more of these in a second with our example problems. But a force, so this is just saying that our weight or our gravity pulling us towards the center of the earth is equal to the normal force. So these two vectors are equal to each other. And when you have equal forces, we call those balanced forces. And that means that this book right here on this table is at rest or it's not accelerating. So it could have constant velocity, but since it's a book on a table, I would say it's at rest. So if this book were moving at accelerating rate, then we would have unbalanced forces. So since we know normal force is equal to the force of gravity or the weight of an object, we can say that normal force is equal to mass times gravity. Another good thing to note here as well is normal force is always perpendicular to the surface that the object is on. So if you have a box on an incline, like in this photo here, the normal force will be pointed perpendicular to the surface that it's on. But the weight is always pulling towards the center of the earth. So it is directly down. So that is why, and I'll make a whole nother video on forces on inclined planes. That's a whole thing in itself. But that is why your apparent weight is lighter on a hill than it is on a flat surface. Okay, let's move on to the next one. All right, our third type of force that I want to talk about, and this is very important, is friction. Okay. Friction is a contact force that opposes motion between two surfaces sliding or trying to slide against each other. Now, the definition says sliding. I would like to say that it's you don't have to slide in order for there to be friction. There's friction in you standing still. Friction is what keeps you from being pulled towards a car. Something has a lot more mass than you. Because remember, smaller things are attracted to bigger things with mass. And friction is what keeps you from being sucked into larger masses. It's always going to act parallel to the surface as well. Same, so it's like the opposite of how we treat it with our normal force. Normal force is perpendicular to the surface. Friction is always going to be parallel to the surface. Now, when we talk about friction, there are two main types of friction. There's static and kinetic. The word static means standing still, and kinetic means moving. So that's a good way to remember how the definition of these two forces. So static friction is the force that prevents an object from starting to move. So it's the amount of force needed to be exerted on an object in order for that object to move initially. The object standing still, I have to exert this certain amount of force in order to get it to move on this surface. It can be represented by the following formula, okay? So this formula says that the force of static friction is equal to the coefficient of static friction. So this would be specific to whatever two surfaces are sliding against each other, perhaps wood on wood, if you're trying to slide a couch around, or feet on grass, or shoes on ice, anything like that, it will have a different static coefficient of friction. And these are usually given to you in the problem. These are set numbers, usually in a table format. So you have the coefficient of static friction, and this is not represented by the letter U. It's usually represented by the letter mu, Greek letter mu, which looks like this. It's going to have a little tail right here with a U. So that's what it looks like if you see it on the internet somewhere. So you have coefficient of static friction times the normal force. So this could be rewritten, since we know normal force is equal to mass times gravity. So you could say coefficient of static friction times mass times gravity is equal to my static force, the amount of force needed to get an object to slide. Now, if we're going to talk about static force, we have to talk about kinetic force, kinetic friction. Okay, so let's scroll down here. Kinetic friction is the force that tries to stop an already sliding object. So if I were moving a couch and it was sliding, it's the force that is opposing me from sliding. If my force dipped below that number, then the couch would eventually slow down to a stop. This can be represented by the following formula. The force of kinetic friction is equal to the coefficient of kinetic friction between the two surfaces times the normal force. So the only difference between the two is the coefficient of friction value that we use there. That's what separates the two formulas. So you need to be careful when you're reading these word problems and realize if is the problem asking me to get something to move, or is the object already moving? Okay, so let's erase these. Let's erase these. Okay. Now moving on to our last force. Our last force here is an applied force. An applied force is a force that is exerted on an object by a person or another object. So if I wanted to go in my living room and move my couch, I would be applying force to that couch, because the couch is at rest. It has a normal force. It has uh, the gravitational force pulling down on it, I would have to apply an external force in order to move that couch because it is at rest. Or if I wanted to speed an object up that's already moving, remember, if something's traveling at constant velocity, it has no net force on it. Net force just means that an object has balanced. Net force is the total amount of force acting on an object. If there is a positive net force, then that means the object is accelerating. If there's no net force, that means the object's either traveling at constant velocity or it is at rest. So it all depends on the net force, how fast your object is accelerating. So just a quick, there's not really a formula that goes with applied force. It just applies to different scenarios. But this is a very common force that you see. This is what you mainly think about as a push or pull, because you can physically do this to any object you want to. You can push on any object, you can pull on any object. It's going to cause the object to be moving. It's either going to be, when we have unbalanced forces, the object's either going to start accelerating or decelerating depending on your net forces there. Okay. So those are the four main forces I wanted to talk about. Now let's get into some word problems down here. Okay, let me get my calculator ready. All right, we're set up. Number one says a person has a mass of 70 kilograms. What is their weight force on Earth? So we're on Earth, so we know gravity is worth 9.8 meters per second squared. So let's write our formula that we want to use. Let's do weight. Is equal to mass, we have that, times gravity. And we know the gravity value on Earth. So we can just go ahead and plug and play straight up here. So 70, that's our mass, 70 kilograms is our mass, times 9.8, so that's the value of gravity, is equal to 686, and the unit for force is newtons. I probably should have covered that at the beginning. It is newtons, named rightfully so after Isaac Newton, who developed those three laws we talked about at the beginning. So that is the person's weight on Earth in newtons. Let's move on to number 2 here. All right, let me erase these scratch marks here. Okay. Number 2 says calculate the gravitational force between two 1,000 kilogram objects that are 5 meters apart. So I want to know the attraction between those two objects. So I'm going to use Newton's universal law of gravitation, which is F is equal to the gravitational constant, G, times mass of the first object times mass of the second object divided by their distance apart, or the radius squared. Now, if I want to plug in some numbers here, it's going to be, G is going to be 6. Remember, this is a constant, so we should already know this. 6.674 times 10 to the negative 11th. So make sure your calculator is in scientific. All right. And then mass 1 times mass 2, they're both 1,000 kilogram objects, so 1,000 squared is going to be 1 million, so I'll just go ahead and write that. Million. Let me put this in parentheses so we don't get confused here. And then 5 squared is going to be 25, so I'll just go ahead and put 25 on the bottom. Okay, now I just have numbers. Now I just need to put them in my calculator and find the force between the two masses. And when you plug them into your calculator, you should get 2.67 times 10 to the negative 6th newtons. That should be your final answer there. Very small force there. Let's move on to number 3. Number 3, we're going to deal with some friction. Let me move it down. There we go. Number 3 says a 15 kilogram box rests on a flat floor. The coefficient of static friction between the box and the floor is 0.6. What is the maximum force you can apply horizontally without moving the box? So I'm going to draw what we call a free body diagram to start this problem. This is a tool you can use to help you visualize forces on an object when we're talking about multiple. It's a great tool. I highly advise that you use it. So I'm just going to represent this box right here. And so you just draw the object. I usually represent whatever the object is with a square. It doesn't matter. You could use a circle if you wanted to, but I use a square for everything. So we always have the normal force. So I'm just going to label that Fn. And the normal force is always going to be equal to our weight. So these two arrows right here, these two vectors should be equal to each other in magnitude. And remember, the arrow pointing down is mass times gravity, or the weight of the object. And let's say I'm pushing the box horizontally to the right. So I have a friction that's opposing my motion. So it's going to be the friction force is going to be pulling me to the left here. And I want to know the maximum force you can apply horizontally without moving the box. So I want to know what the value of this vector here is. So I'm just going to put an X. And this is my static friction force. So when these two vectors here are equal to each other, this is the maximum amount of applied force I can put on the box without it moving. If I put just a tiny, like 0.001 Newton more of force, this box will start sliding across the floor. So this is the maximum amount of force I can apply to the box without it sliding. So our formula that we're going to use to solve this is our static friction force is equal to the static coefficient of friction, which is mu sub s, is equal to the normal force. I can just solve for f sub s here because these two vectors are equal. So I don't really have to plug x into anywhere. So let's just go ahead and start plugging in some numbers here. F sub s is equal to 0.6, because that was given in our problem. And the coefficient of friction is a unitless variable. So don't worry about units with coefficient of friction. Remember, normal force is equal to our mass times gravity, our weight force over here. So we can just say that we can just plug our mass times gravity in here, which is going to be 15, because that was given, our mass of our box was 15 kilograms, times 9.8, which is our gravity value on Earth. We're going to assume that we're on Earth here. So I've got all my numbers here. Now all I have to do is just plug them into my calculator. So I'll do 15 times 9.8, 147 times 0.6, and I should get 88.2 newtons. So that's the maximum amount of applied force I can put on the box without it moving. If I were to apply 88.3 newtons, the box would start moving. It would probably be accelerating really slowly, but it would move nevertheless. Okay, let's do a kinetic friction problem. And just in case if my camera was blocking I'm not sure if it was, but if my camera was blocking the force diagram I did over here on the left, there it is right there. Moving on to number 4. Number 4 says a 10 kilogram sled is sliding on snow. The coefficient of kinetic friction between the sled and snow is 0.15. What is the frictional force acting on the sled? So we just want to know the frictional force, the kinetic frictional force acting on the sled, because as in the problem it said it's already sliding on the snow. So F sub K is going to be equal to the coefficient of kinetic friction of the sled in the snow times our normal force. Okay, I'm not going to do a free body diagram for this problem because we just did one up there, and for the sake of time I'm just going to plug and play for this formula. So if we plug in numbers, we should already have all the numbers we need. It's going to be kinetic frictional force is equal to 0.15 times 10, that's our mass, times 9.8, that's our gravity. We can plug that in there for normal force, because normal forces, remember again, is equal to the weight force, which is mass times gravity. So I have my numbers. Now I can plug into the calculator. 0.15 times 98 is equal to 14.7 newtons. So what does that mean for our sled here? So our sled must, if the force that is being applied to the sled dips below 14.7, the friction from the snow on the sled will cause the sled to start slowing down and eventually stop. But as long as it stays above 14.7, the sled will continue to accelerate and move. Or move at a constant velocity if it's right at 14.7. If it's greater than 14.7, then the sled will begin to accelerate. And it will keep accelerating until something stops it. All right, our last example problem here. I am going to draw a free body diagram for this, so let me go ahead and start with that. A 20 kilogram crate is pushed across a floor with a force of 50 newtons. If the coefficient of kinetic friction between the crate and the floor is 0.3, what is the net force acting on the crate? Remember, net force is just the total amount of force acting on the crate. So let's start with our free body diagram here. I'm going to go ahead and label this with 20. That's just representing the mass. We have a normal force, always going up. If you feel overwhelmed by free body diagrams, just always start with normal force and your gravitational force pulling it down. Those are always givens. Okay, so we have those two. It's pushed across the floor with a force of 50 newtons. I'm going to say that they're pushing it to the right. So our applied force let's do F sub app is equal to 50 newtons. Okay, so that's given to us. And then we have a friction force, and since the box is moving, let me actually make this smaller so I can, oops, I didn't mean to erase that much. All right, let me get back on this pen here. Okay, let me fix this. And since our box is moving, our applied force is going to be less than, our applied force is going to be greater than our friction force. So this is going to be kinetic friction over here, opposing our motion. All right, so let's get into our formulas. We want to know the net force acting on the crate. So we already know that normal force is equal to our weight. So we really don't need to involve these. These cancel each other out. So really we just need to find the friction force, our kinetic friction force. So that's going to be the coefficient of kinetic friction times the normal force. So I lied, we do need the normal force, which is just mass times gravity. But these two do not contribute. What I meant to say is these two are not going to contribute to our net force calculation because they cancel each other out. So if we have all that, let's plug in some numbers. It's going to be 0.3 times 20 times 9.8. Okay, so we have those numbers there. So let's go ahead and calculate that. 0.3 times, let's do this, let's do parentheses first. 20 times 9.8 times 0.3. I should get 58. Our kinetic friction force is going to be worth 58.8 newtons. Okay, so to calculate my net force, I just get the sum of all forces acting on the object. So since I have an applied force and a kinetic force, kinetic friction force that I'm worried about in this system here, I will just involve those two. So let's take our applied force. First off, let me write our equation. Net force is going to be equal to our applied force. Let's do F sub A minus our friction force. Because remember, friction opposes our motion. And when we plug numbers in, we should get an equation that looks like this. F sub net is equal to 50 minus 58.8 And when we plug that into our calculator, we should get negative 8.8 newtons. So what does this mean for our sliding crate across the floor? This means that the crate is actively decelerating or has already stopped because the the kinetic friction force is greater than the applied force, so therefore we are slowing down or decelerating. That is why we get a negative number there. Okay, so that is going to be it for me. I hope you found this video helpful. If you have any questions, leave them in the comments. If there's anything you'd like me to do a video on next, you can also leave that in the comments. And I hope you have a great rest of your day.